So today we will go a little bit more into the detail behind this solar code, how it is programmed, and then I suggest we play around with the exercise 1. So then you can sit here and work, and I can mingle among you and try to help you if you are dead lost. So I say roughly 1 hour, 1 small hour with theory, and then 1 hour with exercise. Okay? We then have a lecture tomorrow morning where I will continue theory with finite differences, also a little bit pointing towards the exercise number 2. Yes? Any questions before I begin? No administrative questions? It's okay? Yep.
Usually, are these hours exercise hours, or is it you mix it up?
I mix it up. In the beginning now it's going to be a lot of lectures, but then it's going to tend more and more and more to exercises, and say mid-semester and out is just exercise. Then it's no more theory. So more exercises in the beginning. More lectures in the beginning. More and more exercises. Other questions? Okay. Let's begin. I just want to check out something. We'll put out the videos on YouTube and provide you with the links. Let's see. It must be there somewhere. Yeah. I can't use the entire blackboard. Don't have a wide angle. You have been given this theory behind the solar algorithm. And here you will have the layout of the computational domain. So this is very essential indeed when you want to reprogram anything. But now let's talk about different meshes or mesh systems in finite difference. You discretisize your domain, make discrete versions of your computational domain, and you will then end up with a mesh system which may or may not be rectangular. So the solar algorithm now, very nice, delta x equals delta y is constant. In the general code, of course, doesn't have to be rectangles, can be any shapes, can be very complex, but we start easy. Question now is where to put your unknowns. How many unknowns do we have? Well, for finite difference, we have in 2 dimensions velocities and pressure. So that's an incompressible code for you. 3 unknowns. Where should we put them? The obvious choice, put everything in the center. So here we will now have 2 velocity components, u in the x direction, v in the y direction, and I put the pressure in the center. This is what's called co-located mesh. Of course, that's where you start. And yes, that was the first thing they tried, and it didn't work. Why? What's the problem here? Well, the problem is the pressure. When you create your discrete versions of the Navier-Stokes, you will have say for the x component of the Navier-Stokes, then you need an equation du dt. I just skip a whole bunch of terms here, but you have the pressure, pdx, and then you have viscosity, double derivative. So that's just a few of the terms in the Navier-Stokes. Make a discrete version of that one. The time derivative we have already looked at in the projection method. Just a forward, first order forward Euler scheme, no problem with him. But here we have a space derivative, and here a double derivative with respect to space. So for a discrete version of that one, what will we have to use? Forget the v's. I need the velocity u. If this now is cell number I and j in the y direction, so then here we have u number I in the x direction. We need him. For the double derivative, you're going to need the center point, and you need a point here, ui plus 1. You need a point here, ui minus 1. So those three, okay, no problem there. What about the pressure? You need a pressure gradient located here. Well, you have a pressure point there, but how to create a derivative at that point? Then you're going to need the pressure here, Pi plus 1, and the pressure here, Pi minus 1. Then you can create a central difference using those two difference and then divided by 2 times delta x. Yes, you can do that. But then you see the pressure I in the center point where you're standing. It doesn't enter the equations. Meaning every other pressure point is decoupled from the solution. So this resulted in very strange pressure solutions. So every other point, like in a checkerboard pattern, can be a totally independent solution to totally different pressure fields, and they didn't talk together. So that was the problem. You could, of course, cheat. You don't have to use a second order accurate derivative. You could have used a forward derivative or a backward derivative or something like that, just to include the center point with the pressure into your scheme. Nowadays you have ways to include it, so co-located meshes are becoming more and more popular again. But in the early days it was discarded. They didn't use it due to this pressure problem. So co-located mesh, that was one option, which you then should know about. You have then a lot of different other versions of it. They tried using velocities in the corners and separating the velocities from the pressure, yada yada yada. What was the most popular mesh was something called MAC. It's marker and cell. So a MAC staggered mesh system. MAC staggered mesh. And this is actually what's used in Sola. So this now is cell number I, J. We put the pressure in the center, P, I, J. The velocities are on the mid surfaces. Here you will have the velocity in the x direction, U, I, J. And on the top you find V, I, J, velocity in the y direction. They call it MAC, marker and cell, because they used these techniques together with a free surface problem. So they put a marker inside a cell, telling that it was a live cell, it was filled with liquid. And then they removed the marker when it was just air, surface, just again a gas. But the goal in that article was this staggered mesh system. So henceforth it has been called a MAC system, marker and cell, from 1967, so it's very old indeed. But this was the first success. And here you see discretizing the Navier-Stokes around the velocity point here. It's very neat to now create a pressure gradient. You have one pressure half a cell away, and then you need the other cell pressure a half a cell the other side to create a derivative in between. Very compact, very neat. Also, you see here, if you want to check the divergence of your simulation, divergence, Mabra dot V vector, and in 2 dimensions, du dx plus dv dy. For an incompressible flow, that one should be 0, unquestionable. How to check it numerically? Well, if you look at this cell, ij, then you can construct these fairly straightforward. The u dx, then you start with u I comma j minus the velocity you have on the other face here to the left. That must be u I minus 1 j divided by delta x. And the same goes in the y direction. The top, that's v I comma j minus, and then the bottom down here, you will then have a velocity with j minus 1 as a location. So it's v I j minus 1 divided by delta y. So that would be one way to look at the divergence directly, which is actually what's done in the Sola algorithm. We check the divergence, and then the philosophy goes as follows. If this divergence, say, is positive, that means you have a net flow out of this cell. Then we reduce the pressure, because then the flow will start to flow into the cell. And vice versa, if this divergence is negative, then we increase the pressure to start flow, that it will flow more out of the cell. Another way to look at this divergence, if you take the surface integral here, actually volume integral, that would now be the divergence theorem. Then you can rewrite the divergence as a surface integral and look at all the fluxes that goes in and out of these 4 phases. You will actually get the exact same recipe, except, well, we can easily do it. So I'm on the side, but never mind. What will it be? The net outflow. I'll do it here. The video don't get it, but never mind. It's a little sidetrack anyway. Net outflow of a cell. Well, Uij, if he's positive, he will be positive out, making a volume flow Uij multiplied with the surface delta y. And then 1 meters into the blackboard to get the dimensions correct. Then you have the volume flow out. Ui minus 1, that's this guy. If he is positive, then he will represent volume flow into the volume. So then That means he's negative. I minus 1j working on the same area. And then the same in the y direction. What goes up? Vij is positive. It will be a positive volume flow out, multiplied with delta x, multiplied with 1 into the blackboard, and finally Vij minus 1 multiplied with the surface delta x. He will be negative volume flow if this guy is positive. And then you now write this one equal to 0. Then you have a net volume flow of 0, as we must have for any domain actually. And you see the equation is identical to this one. You just divide by delta x and then delta y for the entire equation. You see it's identical. So using the partial differential equations directly on a differential form, yes, you can do that, or you can use it on a integral form if you like. Both will work. So the cell, MAC, marker and cell staggered systems, is this one. And of course, this is definitely something you need to have in front of you when you now are going to reprogram the Sola code. So you need this one, and you also need this total computational domain. The way it's been numbered, the i's and j's for all the cells, they are here. And the first live cell, that's this number 22 cell here. Because 11 is part of the ghost cells that we use for the boundary condition. So these are not real cells, they are fictional cells. We just use it for the boundaries. So let us now turn to the code and see how it is programmed. We can find it here. I said it's slow. So this was cell Ij, pressure in the center, velocities to the right and to the top. Vij. It's just a choice. And we have chosen here this one to be Ij. We could just as well have chosen the one to the left as Ij. But as I said, just a choice. Didn't see open. No. Open. He doesn't want to open it. Ah, maybe he's still running. Yeah, so he is. Thank you. A little small, isn't it? Instead. A little bigger. Here is the main loop inside the Sula algorithm for time equals 0 all the way up to maximum time. First double loop here, that's inside the domain. Update all velocities, u and v. These are what we call the tentative velocity field. They are calculated based on the old pressure gradients, and they will in general be wrong. It's not a correct solution, but at least it's a beginning. Then we have the pressure iterations. This was a successive over-relaxation scheme for finding the new pressure and the new velocities. So now we are going to look into, you have it here actually, these loops here, which is then the boundary conditions. Now, for the problem at hand, it was the square cavity system, x and y. So I just make it simple, 4x4 cells. Now this is only the internal cells, the live cells. So we start with number 2, 3, this is now number I, and this is now number n minus, n plus 1 I think, and here n plus 2. Because I want to have it n by n inside live cells. So you see the internal loops, they start from 2 and go all the way up to n plus 1. Meaning number 2, that's the first live cell, n plus 1, that's the last live cell. Then we have number 1 here, also outside. Same goes in the y direction. So the fixtures cells, draw them like this, outside, are meant for the boundary conditions. So now let's check these boundary conditions that is already programmed. For, as it says, for all j's, from 1 to n plus 2, for all j's. J, that is up here, that's the y direction. I, that is the x direction. So for all these, we have written here, u number 1, comma j is 0. U number 1, okay. Cell number 1, they are these fixtures in cells here inside the wall. These are cell number 1. And u, he is located to the right. So u number 1 is this guy. This is u1, comma j. And he is set to be 0. Because remember, the case has been programmed here. It's a square cavity. You have solid walls all around. Everything here should be solid walls. Also this one. So of course he is 0. What about the v number 1? V number 1. That's the velocity in the y direction. V is located at the top. So for this cell, number 1, we have a velocity up here. Half a cell inside the wall. That's not good. I want it to be 0 on the wall. I mean, we have the no slip condition, so no velocity along the wall. But what about half a cell inside the wall? Makes no sense. But we now do the trick, as you can see here. It equals minus v number 2. So that's the trick. If you have a velocity here inside your domain that goes down, then we create another one here, positive, so that you find 0 in between. That's the whole trick. So v number 1 equals minus v number 2. Remember, the velocities inside here, v number 2, that's a live velocity. We have to calculate him. We have to find him from the Navier-Stokes. v number 1, that's part of the boundary conditions. You have to specify the boundary value for him. u1 and v1 has to be specified. And here it's done to create 0 velocity on the wall. On the other side, un plus 1. Which one is that? Well, n plus 1, that's these cells up here. And u for these cells, well, that's to the right. So here we have un plus 1. And perpendicular to a solid wall, of course, he is 0. No problem. What about v? Well, the v velocity for cell n plus 1, well, he's located here. But he's a live velocity. He's supposed to be calculated from the Navier-Stokes. He's not part of the boundary conditions. For the boundary condition, I'm going to need Vn plus 2. So you see it's a little messy with this staggering mesh. Here it's a boundary condition for un plus 1, but here is boundary condition for Vn plus 2. So yes, it's messy, but unavoidable. So yes, we have to specify the velocity in the y direction here, half a cell inside the wall. And we do the same as we did on the other side. Make him negative to the 1, whatever might be inside the domain. So you have 0 in between them. Because we want to have 0 velocity alongside the wall. Any questions so far? Everybody with me on this one? It's just a matter of bookkeeping, but it's quite essential when we now are going to reprogram it. Okay, let's take the x direction here for all i's. So now we are looking at these boundary cells down here. So we start here with the velocity in the y direction. V number I n plus 1. Which one is that? Well, here is 1, 2, 3, n plus 1, n plus 2. So n plus 1, that's this row here. And the v velocities, they are located at the top. Then you are talking these velocities. And of course, they should be 0, perpendicular to the wall, yes. And indeed, they are. And down here, v number I1. Number I1, that's the lower row here of cells. And the v velocity on top of these. Again, 0. No velocity through the walls. Then we have a strange one. U of n plus 2. Which one is that? N plus 2 is this one. So that means the velocity here. We have to specify him. We have to specify him so that we get not 0 here, but we get a velocity of 1. Remember the square cavity test case. The top wall is moving with a velocity of 1. So, say you have a velocity down here. It's called un plus 1. And I want to find him, un plus 2, so that I get a value of 1 in between those two. How should we do that? Well, you take un plus 1 plus un plus 2, and you take the average. Then you should get 1. Okay. Then the boundary condition for the velocity inside the boundary cell here must be 2 minus un plus 1, which is what you find here. So we have constructed boundary conditions so that the top wall is moving with a velocity of 1. Okay? The last one, u1 equals minus u2. u1, that is the bottom cells here. Here is the u velocity. They are equal minus the one you find up here. So if this one is negative, you will find 0 in between. So no slip on the bottom wall. Any questions to these? It's okay? So now we are to reprogram these according to exercise 1. So I will show you how this can be done. So let's see now. Just as an example, I want to simulate the following. Solid wall, and here I make an inlet, like this, and I send in 1 meters per second, or actually everything here is non-dimensionalized, so it's just a velocity of 1. What do we have here on the other side? Well, let's give him a challenge. I put a solid wall here as well. Then what's going to happen? I have an inlet. I force in 1 meters per second. But now I forget the outlet. So hopefully the code will explode. Let's see if it does. Now this was the square cavity test case. No problem here. So now we will reprogram it. First of all, I remove the +2. Then, now the top wall doesn't move. It will be 0. I have removed this average velocity of 1 between those two. Next, I will say the inlet, that's u number 1, will now be not 0, but 1. Let's see if we can find him. That must be this guy. 1. Save and run. Let's see what happens. He's struggling. And you can tell he's struggling. He uses 300 pressure iterations for every time step. That's the maximum allowed of the pressure iterations, trying to solve this Poisson equation. It's not possible. And you see the divergence is totally bananas. But he doesn't crash, strangely enough. Let us crash him and say we don't have to simulate until time t equals 10. We can just simulate 1, just to have a look. So this is sort of a dummy test case. Whenever you get a hold of a computer code, give him a problem like this. You have an inlet and then forget the outlet. And if the program doesn't explode, don't buy it. Of course it should explode. This is a stupid problem. It's not possible to put in liquid in one end and don't have an outlet. And as you can see here, this stream function, here you have streamlines going straight through solid walls. Makes no sense. Of course you can't have flow straight through a solid wall. At least he's been trying to do it, but no, not possible. The pressure, well, not so easy to get anything sensible out of this one. But if you hit this plus button, let's see, here, and then click somewhere, you will have the pressure level. And then you can play around with it. You'll see you have a fairly high pressure here, and well, it doesn't really change much. So here, no, he can't find a solution. And the velocity vectors look terrible, of course. So no, this is not a physical solution. If we had continue, I think he will explode. But never mind that. So what should we have? I need an outlet here. I need an outflow. But I don't know what it will be. So what do we do there? Well, we use the Neumann condition. That was du dn equal to 0, where n now being the direction perpendicular to the wall, or here the outlet. Meaning this is then the x derivative of the velocity. So we have to specify something here, but I don't really know what. Then we say I want the derivative to be 0 here. Okay, I make it simple. I just put these two equal. So for u, what was it? This one is u n plus 1 equals u of n. Let's see if that helps. What was it? U n plus 1 here is not 0 anymore. Is equal to u of n, comma j. What about the velocity in the y direction? We have to specify something for him as well. What should he be? Well, you can take derivative equal to 0 for him as well, saying dv dn equal to 0, Neumann condition, or you could just say he's going to be 0. Both will actually work. What we then are doing, we are forcing the streamlines to be parallel at the outlet. Not necessarily correct, but hopefully it will be better than no opening. So here I just remove the minus sign. So now I have a derivative equal to 0 for v as well. Now let's try to run this one and see what we get. Ah, he exploded very fast. Let's see. Yeah. So when this happens, we just have to use a smaller time step. That's no big deal. Smaller time step. Go from 2 to 1 and see if that helps. Ah, he's still struggling. But you see the divergence is quite small, 10 to the power of minus 7. So now he's sort of managing to solve the Poisson equation for the pressure correctly, at least to the accuracy I have asked for. So now he was okay. For this problem now, the Reynolds number has been set to be 100. So this is probably not correct, but that's something you have to fight with exercise number 1. At least here you see something that is not totally stupid. You send in a constant flat velocity profile. If this domain had been long enough, what should you get on the outlet? Well, you should have the laminar solution for a Poisson parabola. And that means if you wanted then this one to be fully developed, then you need a quite low Reynolds number. 100 is way too big. So he's not finished, he's not fully developed. You'll have a boundary layer here growing, but the boundary layer should grow so that they meet in the center here before the outlet. This is not the case here, but that's part of the exercise 1. Okay, that was the beginning at least for exercise 1. So you have to start programming a little bit. Any questions? No?
Yep.
Yep.
How can you tell if the boundaries are stupid? Like in the first case, it was clear that if you're putting something in and nothing out.
Yeah, hopefully it will explode. I mean, the first simulation I did with the solid wall here, it didn't. I think if I simulated long enough, it would have exploded in the end. Because of course, what's going to happen, you just push in more and more. Of course, something is going to explode numerically in the end. The second one, he exploded quite rapidly, meaning it was unstable. He detected what's called not a number in MATLAB. I have a test in the code there checking if any numbers will be not a number. Should be here somewhere. Yeah, I just add all these solution matrices together and check is there some of them that is not a number, and if so, you just break the simulation. But how can you tell from the simulation result if there's something stupid or not?
No, or from the physical situation.
Again, that is your intuition. Of course, the first one was fairly obvious. It was sort of strangling the entire problem.
Yeah, but for instance, if you put the flow on the upper half in and the lower half out,
Yeah.
you don't know if it will.
No, you don't know. So it can be tricky. For instance, if I do the following, I specify a constant inlet velocity here, and then I specify a pressure here. Along the pressure in these cells is 1. And then I specify the pressure here. The pressure here is supposed to be, say, 0. That will not work. And that's not so easy to see. Remember, here I have now specified a pressure difference. That's a sort of a driving force in the problem. Then you don't know how fast it will flow. That's a part of the solution. If I also specify the velocity inlet as well, then I specify too much. I'm going to strangle the entire code. It's going to explode. Vice versa, if you don't say anything about the pressure, which actually in the Solar code you don't have to. The way it's been programmed is the pressure is not part of the boundary conditions, strangely enough. But if we now say both inlet and outlet, we say derivative equal to 0. So here I have the UDX is 0, and I have the same here as well. Then what's going to happen? Well, anything can happen. But I don't have a driving force in the problem. No pressure difference, no gravity, and I don't say anything about the inlet velocity, so probably I will get just the 0 no-dummy solution here. But I don't know. Try, see what happens. So not always easy to see what's the proper boundary condition for a given problem. That's something, what can remedy that is experience. So start exercising. Other questions? Yep.
In part C, we're adding a forcing term.
Yeah.
Would that be like a pressure?
No. Well, actually, yes, it would be like a pressure, but you are not allowed to use pressure in the Navier-Stokes, in the Solar algorithm. So we add gravity. We just say gravity is 1, since everything is non-dimensional, and it works in the x direction. How do you add gravity into the Navier-Stokes? Well, u dt plus yada yada equals, and then we have pressure, and then we have plus gravity, and then plus viscosity, double derivative. So you just add 1 inside where? Which equation? The entire Navier-Stokes is here, those two, in the x and the y direction. So when you want to add 1, you have to add it inside this parenthesis here. It's delta t multiplied with everything. Here you have the pressure gradient, pressure difference divided by h. You have some acceleration terms, and you have the viscous terms. So just add 1 inside this parenthesis. That's it. Other questions? Okay, exercise time.